Greetings, ladies and gentlemen. Welcome to my short course on shellcode writing for macOS on M1 chips. In this first video, I want to start with a quick overview of ARM64 assembly language. But this is not intended to be an exhaustive introduction to assembly programming, but I rather expect a little bit of familiarity with Intel assembly and use this video to make the transition to ARM assembly easier. Now let's see what we will be talking about in this video. First, I'm going to give a little bit of background on the ARM architecture. Then I will explain how to use the assembler and linker on macOS to test your assembly programs. And then in the main part of the video, I will give a first introduction to the ARM64 assembly language and its features. Some background on the ARM architecture. Originally, the acronym ARM stood for Acorn RISC Machines, named after the company Acorn, which first designed them. That company was founded in 1978, and eventually in 1998 it was broken up, and then the name was changed to Advanced RISC Machines. Nowadays, these processors are designed by a company simply called ARM. And this company does not produce chips itself, but only designs them and then licenses these designs for chip production by other companies. And especially important for us here is the M1 chip design by Apple, which was introduced in late 2020 and is the first chip by Apple with ARM processors that supports the macOS operating system. Previously, it was only supported on Intel chips with the x86, x64 architecture. Now, what does RISC mean? RISC is short for Reduced Instruction Set Computer. And reduced instruction set means that these processors use simple and more elementary instructions than, for example, the so-called CISC architectures, where the C stands for complex instruction set, which is used by Intel or AMD on their x64 processors. And simple and more elementary here means that the instructions that these processors perform usually do only one thing at a time. So, for example, if we want to manipulate data in memory, we first have to load this memory with one instruction into a register, then perform the operation on it, an arithmetic operation, for example, and then write it back into memory. On an Intel chip, you can do these things in one assembler instruction, but on an ARM processor, you would have to use multiple instructions for that. And the downside is that this usually leads to longer programs on ARM processors as compared to an equivalent program on an x64 processor. Historically, ARM chips have been used in low-power computers, such as PDAs or smartphones. And more recently, we've seen them on single-board computers, such as the popular Raspberry Pi. Originally as 32-bit processors, but nowadays we also have 64-bit Raspberry Pis. Even though the main operating system, the Raspberry OS, by default still operates in 32-bit modes, but for example, there are 64-bit Linux versions that can run on the Raspberry Pi. Apple has been using the 32-bit ARM processors originally for their first iPods and iPhones, but eventually in 2013 they switched to 64-bit processors. And now the relatively new M1 chip is a pure 64-bit processor which does not support 32-bit operations. So any data that is to be processed must be loaded into a general purpose register in order to operate on it. And once it has been processed, it must be stored back into memory. We cannot operate on data in memory directly. Every instruction on the ARM architecture is encoded by 32 bits, no matter how complex or simple the instruction is. And the executable code must always be aligned to a 4-byte boundary in memory. Now, this is a bit different from the x64 architecture, where the encodings of different instructions can vary quite a lot, from 1 byte to up to 64 bytes. The ARM64 has 31 general purpose registers, which are named x0 to x30, so this is significantly more than we have on the x64 architecture. And the lower 32 bits of these registers can be addressed by the names W0 to W30. We have some special registers. First, the program counter, PC, which simply contains the address of the next instructions that is to be executed by the processor. So this corresponds to the instruction pointer on the x64 architecture. Then the stack pointer, which simply points to the top of the stack memory. So this is some dynamic short-term memory that is available to us during program execution. The frame pointer, which coincides with the register x29, which points to the stack base during a function call and can be used to recover the stack from a previous function context. Then we have something that has no analog in the x64 world, which is the link register coinciding with x30. And this is used to save the return address at a function call. So when we call a function on ARM64, the instruction address immediately after that function call gets saved into this link register. And once we're done with the function, it gets copied back into the program counter so that program execution can resume precisely after the function call. And another special feature on the ARM architecture is the 0 register, which is simply a register that is constantly set to 0. And this can be quite useful given that very often in a program you need to set some register to 0. And if you don't have a 0 register, this always requires some additional instruction to zero out one of the general purpose registers, but on ARM we don't have to do this because we have this 0 register, which is always 0. And specifically on macOS, the register x18 is reserved, so you should not use it, even though Apple does not state what they use it for. So I cannot tell you that either. The instruction set on ARM comprises the usual arithmetic, logical, and branching operations, so we'll see a few of them later on in this video. And ARM64 offers different levels of privilege for code executions. There are 4 levels of privilege, but 2 of them are relevant for us. One is user mode, which is the least privilege level, and this is the standard for program execution. And then there's supervisor mode, which we need to switch into if we want to execute kernel functions. Okay, how do we use assembler and linker on macOS? Well, I will henceforth assume that you have installed Xcode and the Apple developer tools on your Mac. And then you can invoke the assembler with the command AS, where you feed it as one argument the name of your assembly source file, and then with the -o option you produce an output file with a .o ending. So this means it's an object file, a binary file which contains our assembler program. And I will show you an example of this. Here I have my HelloWorld example. I will quickly walk you through the different parts. I won't explain all of them because we will understand this later on in the video. So the label main here is the entry point for our program, and it has to be declared as global. So it can be made known to the linker that this is where program execution starts. We use the assembler directive align4 to make sure that everything that follows beneath this directive is aligned to a 4-byte boundary, which we recall we have to do. It's executable code, so it has to be aligned to a 4-byte boundary. And now, what do we do? First, I move number 1 to the X0 register. Then I have this label HelloWorld, which is defined down here, which I move to the X1 register. But I use not the move instruction, but the ADR instruction, which tells the assembler that this is an address where this string hello M1 world is stored. And then I move number 16 to the register X2, which is the length of this string here. So the registers X0, X1, and X2 will be the argument for a system call, for the write system call. And the first argument will state where we write to, so standard output, it will just be written to the terminal. The second argument is the pointer to the string we'll be writing, so this is just this hello M1 world string. And the third argument is the length of the string. The next thing we do, we put the value 4 into register X16. So this is a special register which holds the number of the system call we want to execute. And then we use the SVC instruction here to switch to kernel mode, so supervisor mode, and execute the kernel call given by the number in the register X16 with the arguments given in X0, X1, and X2. And as I said, number 4 is the write instruction on macOS. So this part here will write the string hello M1 world to the terminal. And then we end the program gracefully with the exit system call. So we move the return value 0 to the register X0 as the only argument for the exit call. The system call number for exit is number 1, so we move that into X16, and then we use the supervisor call again to exit the program. Now you see I have different arguments for the supervisor call here, and that is just to show that this argument actually doesn't matter at all. It is an optional argument that ARM provides, but it's not used on macOS, so in principle you can put any number you like here. Now let's translate this program into machine code. And there we are. Okay, now I've created a binary file for this assembly program. And if I want to make an executable file out of it, I have to link it with the following command. LD calls the linker. As input file, I give my object file that I created in the assembler. As an output file, I simply write hello for the executable file. I need to use the option -l system to link it with the dynamic libsystem library. And the -l option provides the path where the linker has to look for this library. Just as a side comment, macOS does not allow static linking, so you always have to use this dynamic system library. We can simplify this call a little bit as follows. The first stays the same. same input file, same output file, same else system option, but instead of explicitly writing the full path here, we can use the argument syslib_root, which means this is the path where the linker should search for the library. And then we can dynamically generate the path with this command here. And note, you have to put this in backticks here and here. And this command xcrun is a command that comes with Xcode and the Apple developer tools. And it allows you to find or execute programs from the Xcode command line. So we give it as arguments -SDK macOS X and -- show SDK path, and then it will automatically find the path where the system library is stored. So this is a more portable version of directly writing the path here. And these backticks here, you may or may not know this, but in a shell on Unix, you can enclose an argument for a command line command in backticks, and then the statement within the backticks will be evaluated as a shell command, and the output of that command will be put in as the argument here. So let's see how that turns out. No error message, so apparently it worked. Let's see. Yes, the program runs, so we get the message hello M1 world, and our first macOS assembly program is running. Okay, so now let's look at ARM64 assembly. As I mentioned before, every ARM64 instruction is encoded by 32 bits. And this can lead to larger code than equivalent x64 code would be. From the shellcoder's point of view, this is also a bit unfortunate because null bytes can appear quite easily in these 32-bit fixed length instructions. Another thing is, if our registers are 64 bits wide, but our instructions only are 32 bits wide, how can we even fill 64-bit registers with data? Because a 64-bit argument cannot be fit into a 32-bit instruction. So usually these instructions allow only for data of a size up to 16-bit. And if we want to process larger chunks of data, we have to combine multiple instructions to do that. And here we have two examples of how certain commands are encoded. So here I have a move instruction with an immediate value as an argument, moving into register X0. And note here that immediate values on ARM assembly are always preceded by this sharp symbol. So we want to move the value hex 1234 into X0, and the encoding, the 32-bit encoding for that would look something like this. We have an SF bit here, which is a bit that distinguishes between 64-bit operation and 32-bit operation. And on macOS, this will always be set to 1. So this is something we can ignore. Then at the end, we have a code for the destination register. Interestingly, for the X0 register, that code is not 0, but it's actually 1. Then between bits 20 and 5, we can store the 16-bit value of our immediate arguments. So the hex 1234 would be stored in this region here. Then we have some hard-coded bits here, which simply encode the type of the instruction, the move with an immediate value. And these HW bits here, they give you an interesting feature on ARM, which is called the barrel shifter. And some of the assembler instructions have it. And it allows you to shift the data. So these 16-bit data written to the register can be shifted into the register by either 0, 16, 32 or 48 bits. So there are 4 options, and these can be encoded by these HW bits here. The second version of a move instruction is when we move the content of one register into another register. And the encoding is a bit different, obviously. So the first bits already differ, and we do not have the barrel shifter here because both registers are of the same size, so shifting them doesn't make too much sense. Because registers only need 5 bits for encoding, we have a few redundant bits in this encoding here. Again, the last 5 bits encode the destination register, and now the bits 20 to 16 encode the source register. So this would be to encode X1. And as I said before, the register X0 is encoded by the value 1, and oddly the register X1 is encoded by the value 0. So for this instruction we would actually have all 0 bits here. And now again, from the shellcoder's point of view, this would actually cause a null byte to appear with these fixed values here together with the 0 bits from X1. So that would be problematic when we're writing shellcode. So we would want to avoid using X1 as the second argument in a move instruction. So much for instruction encoding. As I said before, ARM processors cannot operate directly on data in memory. So first we have to load the data into a register. So for example, we load it into X0 and we take the data from the address that is contained in X1. So this is indicated by this notation. The brackets around the register name mean you take the content of the register as an address, and then you take the data that is stored at this address. And the LDR is the load instruction into a register. So once we've done something with this data and we want to store it back into memory, we can use the store instruction, str, taking the data from the register X0 and again writing it to the memory address that is contained in X1. Now, this is a bit unusual for people who are used to the x64 assembly, because here the destination of the memory movement is actually the second argument, whereas in x64 it's almost always the first argument, which is the destination for the data movement. So you have to be aware that this is a bit unintuitive if you're used to x64. We can also access memory at an offset from the value stored in X1. So this is done by simply including a number in the brackets. So we would write load into X0 brackets address X1, but with an offset of 4. So we would take the address in X1, add 4 to it, access the data that is stored there and move it into X0. And the same with the store instruction. If we want to move data between registers or immediate values into registers, we can use the good old move instruction. So straightforward notation. Move X0, X1 means take the content from X1 and write it into X0. Alternatively, take a 16-bit value, always preceded by a sharp, and move it into X0. There's a version of this with an n, so move n, which negates the argument before moving it into the register. So if I had move n, x0, hex 1, 2, 3, 4 here instead of just move, then I would take the bitwise inverse of this value here and move that into x0. So the problem of only being able to move 16-bit values in one instruction can be handled by using the move and keep instruction, or move k. How does this work? If we, for example, have this instruction here, move k, x0, hex 5, 6, 7, 8, and then we have a third parameter, the logical shift left, and by a number n, where n can be 0, 16, 32, or 48. And we take this value, the 16-bit value, and write it into x0, but we shift it by the amount of bits that is given here. So we can divide the 64-bit register x0 into 4 16-bit chunks, and depending on which shift we use here, we can move our 16-bit argument into one of these chunks. And the k here means that we preserve all the previous bits in the register x0. So if we would not use the k here, then all the other bits in x0 would be cleared, and the data that was previously in this would be lost. So with the move k, we can make sure that we indeed preserve what was in x0, other than at the position where we shift this input value to. So, for example, if you want to fill register x0 with this 64-bit value here, we can do it as follows. First, we use an ordinary move instruction, x0 with hex 3210, and that way we move the value 3210 to the least significant bytes in x0. And now we want to shift these 2 bytes into x0. So we want to shift by 16 bits, so we don't overwrite what we previously put in there. And we don't want this to be cleared either by the move instruction, so we use the move k with a shift of 16 bytes, and then we write hex 7654 to the 3rd and 4th byte in the register. And then we go on with the value hex BA98. We move it into x0, shifted by 32 bytes, so 32 bits. So it gets shifted to this position by 8 bytes. And finally, we move FEDC into the register, shifted by 48 bits to the most significant positions in the register. We can use local variables in our assembly code if we declare them by using labels. So this is what it looks like. We can just make up a name for our label, followed by a colon, and then write the data type of the data we want to use and explicitly state it here. So for example, here we use data type ASCII, and we can just write a string as the data, or there are other data types such as byte, where we can give the value of a single byte. We also have word, which would correspond to 4 bytes, and quad, which corresponds to 8 bytes. Yes, it's a bit confusing. You would expect quad to be 4 bytes, but whatever, that's the way it is. Now, if we want to access this data, we have to load the address corresponding to this label into a register, and then can use this register as a pointer to load the data stored at this address into another register. This is how it works. The ADR, address instruction, takes the destination register as first argument and the label as a second argument. So this instruction would load the address corresponding to other label, so the address where this byte is stored, into x1. And then we can use the by now familiar load instruction to take the data at x1 and load it into x0. So after these two instructions, x0 would contain the value hex 12. So how does the assembler deal with these labels? What happens is the label upon assembly gets replaced by an offset value, and that is the offset to the current position of the program counter. And then the address instruction at runtime adds this offset to the program counter, whatever that value might be at this point, and stores this in x1. And so we get a valid address where the data is stored. And by default, these labels get stored in our code section, so they are right next to our executable code. I will quickly show you what that looks like for our HelloWorld program. So here we use the HelloWorld label where our output string is stored. And I can use the objdump disassembly command, so with the -d option on our object file hello.o. And here we see the disassembled codes for our HelloWorld program. So you see it resembles our original source code. It's also quite convenient that we see the binary encoding here. And this line number 4 is the disassembled version of our address x1 HelloWorld instruction. So what happens here? We don't have the label HelloWorld anymore, but we have the number 28. And that's a decimal number 28. So this is the offset of the position of the program counter when it comes to this instruction. So this is offset 4. The program counter would have the value 4 when it comes to this instruction from the beginning of our program. And if we add 28 to 4, then we get 32. Now, the addresses here are in hex values, so 20 hex is actually 32. So this is precisely the beginning of our HelloWorld string. Okay, so the program counter is 4, and the address instruction simply takes the program counter, adds the offset 28, which points to this data down here, and moves that into x1. We also have the usual arithmetic operations on our assembler, adding, subtracting, multiplying, and dividing, where we have both signed and unsigned division. And the scheme is the same for all of them. So we have 3 registers as arguments. The first one is the destination register, the second one and the third one are the operands. So add x0, x1, x2 would mean take the values in x1 and x2, add them and store them in the x0. And sub x0, x1, x2 would mean take the value in x1, subtract the value in x2 and store the result in x0. And similar for multiplication and division. We have logical shift operations. We already saw them used in the barrel shifter with our move instruction, but we can simply apply them by themselves to registers. So it's quite straightforward. So LSL stands for logical shift left, applied to a register by n bits, and LSR, the logical shift right, with the same syntax, shifts the register to the right by n bits. Here we have a small example. So assume we move the value hex 0f into the x0 register. And if we shift it by 16 bits to the left, well, then it looks like this. 16 bits become cleared and the value 0f0000 hex is now the value in x0. And then we can take this again and shift it by 8 bits to the right. And the resulting value would be 0f00 hex. ARM64 also supports the usual bitwise logical operations AND, OR, and exclusive OR with these mnemonics. Curiously, the exclusive OR is EOR and not the more common XOR on ARM64, so make sure not to forget that. If you use two registers as arguments for those, then they work as you would expect. So one register holds a bit mask that gets applied to the other one, and then you perform any of these bitwise operations. If you want to use immediate values as a bit mask, then it gets a bit complicated, because we remember we only have 32 bit wide instructions, so they couldn't possibly hold a 64 bit wide mask for the bitwise operation. So ARM came up with a rather bizarre scheme to encode these bit masks, and I have no intention of getting into that, so I'll just skip over that, but I will give you a link in the box below where you can look up how this works. Then, controlling program flow. As in x64 assembly, we would use a compare instruction for logical comparisons. And the outcome of this compare would set certain flags on our processor. So we have 4 flags: the negative flag, the 0 flag, carry flag, and overflow flag. And then we can control the program flow through conditional branches with the syntax b.condition. So b is always for a branch instruction, and the dot indicates that this branch instruction will be dependent on a certain condition, so on the state of these 4 flags. And when this condition is satisfied, the branch will be taken, and if it's not satisfied, the branch will be ignored. Here's a simple example of a while loop that runs as long as x0 is greater or equal to x1. So we have the loop label, which is the beginning of the loop. We compare x0 to x1. And then we have a conditional branch, b.cc, where cc stands for carry clear. So if the carry flag is 0, and this corresponds to the condition that x0 is strictly smaller than x1. And if this condition is met, then we jump to the label end loop, which is behind the loop body. So that would mean we terminate the loop. Otherwise, we ignore it, do whatever the loop does, which probably would somehow affect the values of x0 and x1. And then at the end, we have an unconditional jump back to the beginning of the loop. So we perform the whole thing again. And we do this until at some point this condition is met, and then we jump out of the loop and continue with program execution, whatever comes later on. I have modified the HelloWorld example a little bit, and yeah, it's just a bit of a silly modification, not something very meaningful. What I'll do, I'll run through a loop, and in each iteration I will output one more character of this string until in the last iteration I'll output the full string. And when that is done, the condition to end the loop will be met and we terminate the program. So let's see what I did here. First, I initialize the parameter x2, that's the argument which holds our string length, with 0. So I do this by moving the 0 register, x.r, here into x2. Then I have my loop label here. So here the loop begins, and I begin by comparing x2 to the value 16. And then I use this conditional branch b.cs to jump to end loop if the condition that x2 is strictly larger than 16 is met. Okay, so while x2 is smaller than 16, I will ignore this jump and go through the loop. And then when I reach the end of the loop, I will do the unconditional branch here to jump back to the beginning of the loop. And what I do in the loop, is the following. First, I increase x2, so starting out with 0, then adding 1. I move the standard out argument into x0. I move the address of the HelloWorld string into x1. I move system call number 4 into x16, and then I switch to supervisor mode to execute this system call. So the 3 arguments will be standard out, address of HelloWorld, and the length of the string will always be 1 more character in each iteration. So I placed the new line character at the front, so we get a proper output here. And once the loop is done, we again use these commands here to terminate the program. Let's try it out. Yeah, that worked. Link it. Yeah, and we see we start out with just outputting the new line character, so we don't see anything here, just another new line. And then on each iteration, we output 1 more character of our string until we output the full string. And then the loop terminates and the program ends. Also very important for assembly programming is the stack, which provides a data structure for short-term memory allocation at runtime. It works by the last in, first out principle, so the data that was put on the stack, the last, is going to be the one that is taken off the stack the first. As in the x64 architecture, the stack grows towards smaller addresses in memory, so the top of the stack is actually the smallest address on the stack. And every entry of the stack is 128 bits or 16 bytes wide. So note, this is twice the size of a register. So one entry can hold 2 registers. The stack pointer contains the address of the top of the stack, so as I said, the lowest address on the stack. And the stack pointer must always be aligned to a 16-byte boundary. There are no explicit push or pop instructions on ARM64, so we have to emulate them using store and load instructions. And there are some special features for these store and load instructions that allow us to change the stack pointer while storing and loading. So that makes it easier. And the first instruction here is basically a push to the stack. We take the value in register x0. We store it at the address of the stack pointer, but with an offset of -16. So we go 1 address lower, which means we put another entry on top of the stack. And then we use this exclamation mark, which causes the stack pointer to actually be decreased by this value here after we perform the store. So this is precisely what a push to the stack does. And the pop of the stack is as follows. So here we load into register x0 the value that is at the address of the stack pointer. And once we've done that, this third argument indicates that we should increase the stack pointer by 16. So we lower the stack towards higher addresses. Now, registers are only 8 bytes wide, but the stack entry, as I said, is 16 bytes wide. So if we push only 1 register with an instruction like this, it would waste space on the stack. But there are instructions to actually push or pop 2 registers at once. So this can actually save time and memory, because you would replace 2 push instructions by just 1. And here we don't use the usual store and load, but we use store P and load P. So P for pair, because we can push or pop a pair of registers. And it would be written like this: store pair x0 and x1 to SP decreased by 16. And the pop would be load pair x0, x1. So we take 16 bytes off the stack, write the first, so the lower 16 bytes, lower 8 bytes to x0 and the higher 8 bytes to x1. And afterwards increase the stack pointer by 16. Here's a short illustration how that works. So first I just push a single register and then pop it into a different one. This is our stack, so the region where the stack memory is allocated. The stack pointer points to the top of the stack. The dots just indicate that there's some data that we don't care about already on the stack. It's 16 bytes wide, so the size of 2 registers. And it will grow to lower addresses, as I said before. So if we pop something on the stack pointer will point to this chunk here. Now, first I move the data hex 1, 2, 3, 4 into the x0 register, and then I will push it onto the stack with the second instruction here. So it gets written to the lower order 8 bytes on the stack. So this part here is undefined, so whatever data might have been there in this piece of memory will still be in there. But yeah, we have no control over that. It's wasted space for all we know. And now I pop this entry into the x2 register, which means the stack pointer gets decreased again. x2 contains the value hex 1, 2, 3, 4 as well. And yeah, it still remains in memory here, but not within the valid stack region. So again, as far as we are concerned, this is undefined data now. And by comparison, let's look at the pairwise push and pop. So here first we write hex 1, 2, 3, 4 into x0. Then we write hex 5, 6, 7, 8 into x1. And then we use the pairwise push, which takes the first argument to the lower order bytes in the stack entry and the second argument into the higher order bytes. And then we pop it off as a pair into x2 and x3. So the 1, 2, 3, 4 hex goes into x2 and the 5, 6, 7, 8 hex goes into x3. One thing we have to be aware of is that Apple uses the little endian format to store data on its M1 chips. Now, in general, ARM does not prefer either little endian or big endian, but it depends on the particular manufacturer which format is chosen as a standard. What does it mean again? Little endian means that the first byte in a chunk of data gets stored at the lowest address and the last byte gets stored at the highest address. So this can be confusing if we write down the data for us to read, because we often interpret register contents as hexadecimal numbers, and the highest value digit is represented by the highest order byte. And we read numbers from the left to the right. So the first number we read is actually the highest order byte, but that would be the one at the highest address, the last byte in our stream of data. So to make clear what I mean, look at this example. We have this string /bin. So this is 4 bytes long. /bin is, you could say, an important part of a string, because this is the directory on Unix machines where the standard executable programs are stored, and we will use this also in writing shellcode. So this is 4 bytes long, and we want to store it in the register x0. So the hexadecimal encoding is slash hex to F, B hex 62, I hex 69, and N hex 6E. Now, because the slash is the first byte in this string, it will be stored at the lowest address. Then at the second lowest address, the B will be stored, at the third address I, and at the highest address the N will be stored. Okay, so the first byte from the left to the right is at the lowest address. However, if we read this as a hexadecimal number, we reverse the order, because the last byte at the highest address corresponds to the highest order digit in the hexadecimal number. So it would be read like hex 6E, 69, 62, 2F, where 2F corresponds to the slash. So there are two representations of this in little endian. In memory, we would usually write the lowest memory addresses to the left and the higher ones to the right. And so the order would be 2F, 62, 69, 6E, just like we would write out the string slash bin. But in registers, we usually represent them as hexadecimal numbers, where the highest order byte is written on the left, because that's the way we write numbers, and the lowest order byte is on the very right. So here we would write this number as 6E, 69, 62, 2F, so just in the reverse order. And if you use a debugger to analyze your programs, you will find representations in both ways, and that can be confusing at times. But be aware, Apple uses little endian. The big endian format would be just the opposite way of storing the data, which has some disadvantages, but it is also used quite often. For example, the Internet Protocol uses the big endian format. So that's something you should be aware of. And when you do network programming and want to send data over the internet, you have to use some API functions to convert little endian to big endian. To illustrate the use of the stack and the little endian format, I have yet another modification of our HelloWorld program. And what I do now is I will no longer load the HelloWorld string from this label down here, but instead I will use this bit of code up here to write it directly into registers and then push it on the stack, and then take the address from the stack as an input argument to the system write call. Now, before I explain this program, I will assemble it and look at the binary code, so we can actually understand the little endian format a little better. Let's first check if it still works. That seems to be the case. Okay, so here we see our HelloWorld string in memory. And as I said, we won't be using this one anymore. It might be helpful to add an additional view, namely just the raw hex dump of our object file. We can get this with the -s option for object dump. So here we don't see the disassembled code, but just really the raw bytes of our assembled program. And on the side we see the ASCII interpretation. So here's our hello world string corresponding to the bytes here, beginning with 0A for the new line character, which can't be seen on the right, and then hex 48 for the capital H. Now, what do I do here? Again, I have this loop to output the bytes one by one. And that hasn't changed from the Hello 2 program. But here I have some code to place the Hello M1 world string directly into the registers. And then I will push the registers X8 and X9, that's where I store the string, to the stack. And what I will do then, I will move the stack pointer into X1. So because once I push these two onto the stack pointer will point at the hello world string because it's on top of the stack. So I can use the stack pointer as the address for my string. I'll move it into X1 because that's the output. And as usual, I'll use standard out as the argument for X0. System call number 4 into register X16 and then switch to supervisor mode to write to the terminal. Now, how do I do it with the stack? Recall one stack entry holds 2 registers. And it just so happens that we can fit the whole hello M1 world string into 2 registers. That's quite convenient. So how do I come up with all these values that I store into X8 and X9? Well, we can look at the hex dump. As I said, this hex code here corresponds to our hello M1 world string, beginning with the new line character 08. And in this order here, we go from lower addresses to higher addresses. So that here you see the new line character is the first one in the string, so it stands at the lowest addresses. But that means because we write data to the register in the form of hexadecimal numbers, the lowest address digit, 0A here, has to be the least significant byte in the register. So this is why we write it on the rightmost position here, followed by the second byte, the capital H, for 8. And we can at any time only put 2 bytes into a register. I explained that before on the slide about the move case. So we take the 2 least significant bytes in reversed order, little endian, and move them into X8. Then we take the next 2 bytes, 6.5 and 6C, again in reversed order, move and keep into X8, but we shift them by 16 bits. So those 2 bytes get moved to byte positions 2 and 3 in X8. Then we take the next 2 bytes, 6C, 6F, but again in reversed order. Move and keep into X8, but now shifting by 32 bits. And finally, we move the last 2 bytes, 20, 4D, in reverse order, 4D, 20. So we only reverse the order of the bytes, but of course we don't reverse the digits within 1 byte. So we take 20 and not 02. Don't mix this up. So we take 4D, 20, move K into X8, left shift by 48 bits. So then we have stored this part in x8. And now we do exactly the same with this part, storing it in x9. And so x8, x9 together will contain the whole hello M1 world string. We push them onto the stack in this order. So x8 takes up the lower order bytes in the stack entry, and x9 takes the higher order bytes in the stack entry. So now the stack pointer points to the top entry where we have exactly our hello M1 world string positioned. And then we go into the loop, and as I said before, we can now use the stack pointer as the address of our input string, and then everything goes as we did before. And as we've seen, this does actually work as expected. Now let us look how function calls work in ARM64 assembly. A function call is executed via a so-called branch with link instruction, or BL. And this instruction uses the link register to save the return address. So this means when we execute the branch with link instruction, we first save the value of the current program counter plus 4 bytes in the link register. So this is the address of the instruction that comes right after the branch with link. So once the function we call is done and we return, we can read out the value in the link register and return to the address right after the function call and resume program execution there. Now, once the current program counter plus 4 is saved, we replace the program counter with the argument of BL, of the branch with link, which in assembly usually will be a label. And then program execution resumes at this new address, which is now contained in the program counter. So this is the address where the function we're calling is located in memory. Once the function is done, we will use the return instruction, ret, to copy the content of the link register back into the program counter. And thus we will get back to the instruction right after the branch with link and resume where the function call left off. The calling conventions on ARM64 is as follows. Before we do the branch with link, we push any registers that need to be preserved for after the function call onto the stack. Then the first 10 arguments for the function are stored in the registers x0 to x9. And if we should have any more arguments, we will push them on the stack. Then we execute the branch with link and run the function, do whatever the function is supposed to do. And at the end of the function, we will place the return value in the register x0 and then execute the ret instruction, which, as I said here, copies back the link register into the program counter, so we resume where we left off at the branch with link. Then we evaluate the return value in x0, and after that we pop any previously saved registers. Now on x64 we're used to using the stack to save the instruction pointer with our return address, and we only need the stack when we have nested function calls. So assume we're using branch with link to call a first function, and then within that function we will call another function. Because we only have one link register, that would overwrite our previous return value and it would be lost. So of course we have to then save the link register on the stack before we do the nested function call. And once we return from the nested function, we have to pop it off the stack back into LR and fix our return value. Now, I want to demonstrate this with another little assembly program. Here, I modified HelloWorld so that I do the right system call from within a function. Now, how does it work? Here's main. Here's the entry point for my program. And the first thing I do is a branch with link to the hello function. So this is the label I use to declare my function. And yeah, you see it's this whole piece of code down to this return instruction here. And the only thing I do is really call this function and then I exit the program. And so I moved my whole code just into this function. And I'm not giving any arguments to the function. So just to demonstrate that this branch with link works and that the return works properly, let us try this out. And we link it. And it still works. So we see the function call worked nicely. Maybe just for the fun of it, we do another object dump. Yeah, and here we see the label hello function has been replaced by an offset from the program counter by hex 10, so by 16. And yeah, that's precisely this address where the hello function begins. Finally, let's understand those supervisor calls we've been making all the time in order to get kernel functions to work. So if we want to execute a kernel function, or also refer to, as I've done so far, as system calls, we must change the privilege level from the normal user mode to supervisor mode. How do we do this? Every kernel function is identified by a unique number, and this number is, as we have seen by now, placed in the register x16. And then we execute the supervisor call svc with some number n as an argument to switch to supervisor mode and execute this kernel function identified by this unique number in register x16. Now, oddly enough, this argument here for svc is irrelevant on macOS. So ARM gives the developers an option to specify an argument here and use this if they see necessary, but macOS does not use this number apparently, so you can put in here whatever you want. Sometimes you will find hex 80 as for this number, which is reminiscent of the 32-bit Linux system calls via the interrupt hex 80, but it doesn't have any meaning for us. And yeah, it's only if you want to make it explicit that your system call by being reminiscent of these Linux codes. What I do, I usually take a high number, for example, hex FFFF, because that way I can avoid null bytes getting into the encoding of this supervisor call. But as I said, in principle, you can take any number you like. And the calling conventions for kernel functions or system calls are the same as for regular functions. The arguments, the first 10 arguments are put into registers x0 to x9. Any further arguments go to the stack, and the return value is placed in x0. And just to show you that it doesn't matter, it really doesn't matter which value we use here. Let me just mess around with this value here. Let's set it to 0, for example. And here we set it to, say, 1, 2, 3, 4. We assemble and link our files again. And it still works. So nothing changed when we changed these arguments for the supervisor calls. So yeah, that's not important. Now, as I said, supervisor calls are determined by a unique number, and you may ask yourself, how do I find this number? You can find it locally on your Mac by looking for the file /sys/syscall.h in some directory. For example, one of the directories is this one. So I suggest you simply use locate syscall.h and you will get a bunch of directories that include this file, and then you can use cat to have a look at it. So you see we got quite a few of them here. Copy that. And here we see all the syscalls listed with their numbers. It's not very convenient to read due to the sheer number, so you could use grep to make it a bit more readable. So say we are looking for the connect system call, and we can just grab connect, and we only get those system calls that have connect in the name. This will be interesting when writing shellcode. Alternatively, you can look up these codes on the web, because Apple actually supplies the source code for its operating systems, at least some not completely recent versions. So the latest version that I'm using apparently is not available, but you can navigate to this internet address here, and then you get the source tree of macOS, and there you can navigate to the subdirectory bsd/kern/syscalls.master. And this file not only contains the system call numbers, but it also contains the function declarations in C, which is quite helpful if you want to know which arguments you have to feed to your system call. So you see the data structures and the number of arguments that you need to hand to a system call, and it's quite convenient. Let me show you how to find the system call numbers in the macOS source code. So here we are at the address opensource.apple.com/source/xnu, XNU being the macOS kernel, and we choose the latest version. So there are a bunch of directories here, and we're interested in the BSD one because the system calls we're using are taken from the BSD part of macOS. We go into BSD, then we go into subdirectory kern. We locate the file syscalls.master. And here we are. We have all the system calls with their numbers and with their function declaration in C style. For example, let's look at the connect function again. Here we again see system call number 98, which is consistent with what we had before on our own machine. And we also see the arguments here, s, name, and name length. So that in that particular case would be a socket number. Then, yeah, the name of the machine to connect to and the length. Okay, so now you know how to find system call numbers, and that's the end of my quick overview of ARM64 assembly programming. In the next video, I will show you how to write a bind shell on macOS using what we learned in this video. And after that, I will show how you can write a reverse shell. You know what to do in the YouTube world. Like, subscribe, and thereby motivate me to produce more content. Thank you very much for watching.